put on the presentation mode. Hello, everyone. Today, I'm going to talk about accelerating transceiver characterization and verification. So first, a brief introduction to Tektronix. So Tektronix is a test and measurement company, a pioneer in the manufacturing test and measurement equipment, founded in 1946 and later acquired by Danaher in 2007. And after that, in 2016, by Fortive Corporation. So the headquarters is in Beaverton, Oregon. So it has many patents, and Tektronix manufactures oscilloscopes, signal sources, and spectrum analyzers. In year 2010, Tektronix acquired Keithley. So Keithley manufactures the source multimeters and semiconductors test characterization. So here you see a summary of the products. From the right, you see the sampling oscilloscopes and clock recovery. You see the real-time oscilloscope. After that, there is an OMA light wave signal analyzer for coherent application, a spectrum analyzers, a wafer tester for the characterization of semiconductors at device and wafer levels, arbitrary waveform generators, as well as the parameter analyzers. So what are the key bandwidth drivers which urges us to address the bandwidth requirements of the customers? So what we see here is an estimated amount of data creation used in different platforms in 60 seconds in 2020. So this trend keeps increasing on a yearly basis. So if you look at top right corner here in YouTube, you see that the user uploaded 500 hours of videos on YouTube. Furthermore, if you look at Netflix here, you see that almost around 400,000 videos were streamed in a minute in the last year. So that's a huge amount of data transmission from a cloud. Also, our daily life has been impacted by COVID. So during this time, we tremendously relied more on online activities. From the infographic, the data traffic explosion in each sector is conspicuous. So you see that in each sector, there is a drastic increase. Obviously, everyone switched to the home office, or they remotely work right now, and there are lots of online meetings. So, for example, we see that the data and traffic in this case, in this sector, is increased more than 2,000%. So that's a huge amount. So if we look at the market growth in silicon photonics, you see the infographic here. This is a forecast for 2019 to 2025. So on the left side, you see in year 2019, there were almost $480 million investment in two sectors. So green shows the data center transceiver sectors, and yellow is the long-haul transceivers applications. So the forecast anticipates that till 2025, there will be a 40% of increase in CAGR. And the main contributor will be the data center transceivers here. The investment is anticipated to be $3.9 billion by 2025. So what needs to be done? Of course, in order to address this bandwidth requirement, we need to come up with more advanced technologies. So we need one is to use more complex modulation formats such as PAM4 or higher modulation formats such as QAM. So PAM4 for direct detect technology and QAM for coherent technology. So on the right side, you see that in order to cope with this bandwidth hungry application, you need to either have higher number of lanes, or you need to just go higher with the line coding and use more complex modulating formats such as PAM4 and coherent applications. So in this way, you might be able to address the bandwidth demand. On the right side, you see two standards here. So one is 400G base DR, which is our discussion here, based on the 4 lanes for data centers, and the other one is based on 8 lanes, 400G base LR8. Here is a quick overview of the Ethernet standards. On the right side, you see the table, electrical as well as the optical standards from 1983 to date. We see the standardization in red for electrical as well as optical cases. We are going toward 800G base and 1.6 terabit internet. On the left side, you see the history of the module development. So from the SFP to CFP for the coherent, and we have now QSFP, DD, and OSFP for the current applications. So increasing complexity of these devices require a comprehensive test that enhances the amount of time for device to be tested. So the suppliers are realizing a steady upstick in the test requirements and an increase to the amount of the time that a device needed to be tested in the manufacturing facility. So this means that the devices are being tested longer than the heritage devices, because now we have the more complex transceivers. That's why the device then under the test causes a higher cost without a proven reliability track. So this is due to the modulation format and shift from NRZ to PAM4. So in case of the PAM4, the test time increases by a factor of 10, and the errors need to be corrected with more number of equalization taps, and it has a less SNR margin compared to the NRZ. This means that this would increase the test and the characterization of devices in the manufacturing floor. So what changed between the previous standard and the current standard? So in previous standard, we used to measure the mask, transmitter I mask, optical modulation amplitude and extinction ratio. But now we have the PAM4 modulation format. So there is a new definition by the standard, which is called TDQ, is an important parameter to be tested. Basically, it shows how good your transmitter is. Now we have the optical modulation amplitude outer, we have the extinction ratio, and we have the level separation mismatch ratio. So all these parameters need to be tested under different conditions. So briefly, just allude to the difference between the TDQ and NRZ. So before, in previous standards, the people used to measure just the I mask in NRZ line coding, but right now there is a more complicated parameter TDQ, which needs to be tested on each device, on each module, which causes to take more time compared to the NRZ test. So here we see an example The table exemplifies the cost per device based on estimated tested time and the station cost. So our main message here in MASSTART is to reduce the cost of manufacturing of the transceivers which are being developed in the framework of this project. So you see an example on top. So these are in K dollars. So these are just an assumptions. So assume that we have a test station which costs $150K and your test time would require 120 minutes. So in this case, each device costs for you $45. But if you come up with an idea which reduces your test time, thereby reducing or making accelerating the speed time, so this reduces your manufacturing cost. As an example, if we assume that the test time would take 15 minutes, so in this case, you reduce the cost per device about $5.6. So why this would help the manufacturer? First of all, this facilitates the manufacturer to go to the market faster. This also increase the throughput and reduce the capital expenses, which is a critical concern of all manufacturers. Additionally, it also meet the customers' requirements, which they need to also address the demand of their own customers. So they need to get the devices as fast as possible. So Tektronix is conducting a research to adopt machine learning in order to reduce the speed of all these parameters defined by the standards during the characterization as well as the manufacturing. So the machine learning has been recently seen with this popularity in optical communication. That's why it's really important in order to be able to cope with the high cost and to address the reliability concerns. So machine learning now is under the investigation by Tektronix. So how does it work in terms of the PDQ measurement as an example here? So basically, it gets the waveform which is acquired by the Tektronix sampling oscilloscope or real-time oscilloscopes. And then based on the algorithm, then it calculates the PDQ, which results in the computation speed improvement of 20 times faster than the classical PDQ computation time. So I would like to show you a video which compares the classical as well as the machine learning PDQ. So here what you see is the GUI of the optical sampling oscilloscope of Tektronix. So what we see here is the TDQ measurement calculation, as well as all necessary parameters in PAM4 application for 400G DR4. So what we see here now, TDQ is measured based on a traditional algorithm. So it took 7 seconds for one device and one lane. In the next acquisition, 6 seconds almost, and again 6 seconds. And it takes almost 6 seconds. Now we turn on the machine learning algorithm, and you see the difference between the speed. So this is now the TDQ machine learning. So as you can see, it's so fast that you see almost the factor of 6 here, for example. And it must be mentioned that the speed is almost in a matter of milliseconds if we ignore the speed of acquisition. So that helps the manufacturer in their manufacturing floor to accelerate the characterization while reducing the cost and capex. So this is my last slide. I think I'm on time. So thank you very much for your attention.